Control V. Okay.
Okay, I'm here.
Ah, good. So how is the situation in Prague, Edward?
I'm in Germany.
Oh,
I'm in Mainz. I escaped from Prague.
so is it allowed to travel? I mean, you are allowed to travel now?
I left Prague at the end of September. No, we are allowed to travel. The problem is the country where you go. So I went to Germany. So in Germany, when I left, the only condition was to pass the test on COVID.
I see.
So I passed the test on COVID the 1st of October in Germany, and then I could stay in Germany.
Ah, okay.
Now they change the rules. Now you if you come from Prague or some what they call the risky area, you have to stay 5 days in quarantine, and at the end of your quarantine, you have to pass the test.
Ah, that's too much here.
This is the German rule, right? But I already escaped. I'm now in Germany, but you know they have rules even inside Germany. So I was planning to go to visit Martina Hofmanova in Bielefeld, and I'm in Mainz now. And Mainz is now considered to be a risky area. And so it's not clear if I can go to Bielefeld. It's crazy.
I see.
I can go, but they can put me in quarantine there.
Uh-huh.
Well, I hope not, but well, I hope in the worst case they will ask me to pass another test, which is, I mean, in Germany, you know, in Prague now there are many cases. So if you, you know, there are lines, there are queues. So it's even dangerous if you wait there, because of course you are waiting with potentially ill people. And here in Germany, there is at least here in Mainz, there was nobody. So I just went there. They tested me. It took me like 2 minutes, and that's it.
I see.
Yeah.
Okay,
so start or
yes, sorry?
yeah, can you hear me well?
Yeah, we can hear you. So I'm just wondering.
Okay. So I'm ready to start. Just let me know when I should start.
Yeah, so we start now, yeah.
So you can see the slides.
Sure, yeah. So welcome everybody. It is my honor and privilege to introduce our speaker today, Professor Eduard Feiereisel from Czech Academy of Sciences. So Professor Feiereisel is a professor of mathematics in the Institute of Mathematics of Czech Academy of Sciences. So he is a renowned specialist in the mathematical theory of fluid dynamics, whose expertise has been recognized by many awards, the latest being the Bernard Bolzano Medal. He has several fundamental works in this field. So in particular, his fundamental work on compressible Navier-Stokes equations, where he improved the result of Lyon, and his work on complete Euler systems are highly cited. So he has published more than 300 research publications, including several highly cited publications in prestigious journals. Today, he is going to talk about S convergence and approximation of oscillatory solutions in fluid dynamics. So let us welcome Professor Feiereisel, and over to you, Edward.
Okay. Thank you very much. Thank you very much, Ujjwal, for this nice invitation. I mean, it's a kind of advantage of COVID that you can give talks in many different places during 1 week. Actually, I gave several talks this week in very distant places. Now I'm in India. So the goal is to speak about S-convergence. This is a joint work with several people. You can see my co-authors on the slides. These are co-authors of several papers. Maybe I did not mention a complete list of them, but you will see in what follows. Well, S-convergence is a kind of concept. This is not completely new. If you are familiar with concepts like statistical convergence or Cesaro mean convergence, it's very much related to that. If I a little bit simplify, I would say that this is something like Cesaro means convergence adapted to the framework of Young measures. And so, of course, it's a purely theoretical tool. I will not show you any kind of very practical applications. However, the goal to develop this technique comes from numerical analysis. In particular, if you solve certain problems concerning perfect fluids, we will see the Euler system very soon. Numerical methods in certain regimes may exhibit oscillations. Now, of course, numerical analysts, they know that oscillations is not a good phenomena. They would say, okay, so the method is not good. Well, on the other hand, we know that for certain data, at least, or in certain regimes, the system we are computing is not really like a correctly posed problem, which means that the result is very sensitive with respect to the initial data, for instance, and even the system itself may not have a unique solution. I mean, there are analytical proofs. I will speak about it later. And so it might be that what you see in what the numerical method gives you, what the oscillatory sequence, is not really a fake, but this is the real behavior of the fluid. That really in this regime, when the viscosity, for instance, approaches zero, the fluid starts oscillating. And the proper tool to describe these oscillations is no longer a single valued function, but a measure, which typically in the context of PDEs is called the Young measure, which kind of characterizes the probability that your state functions or state variables will be ranging in a certain part of the phase space. However, we find out that the Young measures are not so convenient. So basically computations in this direction were performed by Sid Mishra, who was one of the last speakers, and his group, and also in collaboration with Eitan Tadmor, where they really computed measure-valued solutions to all that system. However, they have a different approach because they sort of approach the data statistically. Well, in this, and what I show you here, we have the data that are fixed, and what will be averaged, or where the statistic will be done not on the data, but on the step of the numerical approximation. But we will come to it later. Let me start with two motivated examples. There is certain analogy of what I am talking about with other branches of mathematics, and the most prominent one is the so-called strong law of large numbers from the probability theory. It's actually very close to what I speak about now, or what I will speak about now. So let me remind you what it is. Strong law of large numbers tells you the following. Assume that you have a sequence of functions. Well, they call them random variables, which is nothing other that they are measurable with respect to some measure, and so are defined on some probability space, which is where the measure is normalized to be a probability measure, so it's normalized to be 1. The crucial assumption is that they are independent. I do not want to spend too much time on explaining what it is, but it's really important. And they have the same expectation, which again means that the integral of them over the probability space is the same, if you don't like to mix it up with probability. And then the claim of strong law is that if you take the average, what is called Cesaro average, you take the mean, you take the first n of them and divide by n, then this is going to converge as n goes to infinity. But the main point is that the convergence is almost surely, which, or if you want in the theory of normal functions that you may obtain in numerics, almost everywhere. And this is very good because the almost everywhere convergence, of course, it's something you can compute, you can see. Oscillations, so the sequence itself can be oscillatory in the sense that it could be, for instance, sinus and x or something similar. And these are independent random variables. And now, but the sequence, the sum itself converges strongly. So the message is, if you compute the sums, you can get better results with respect to convergence. A second example is also somehow related, and this is a kind of generalization of this strong law of large numbers to the context of not necessarily independent random variables. In a probability theory, there is something what people call a subsequence principle, which means that suppose that you have a statement which holds for independent sequence, then typically the same statement holds for a subsequence of any sequence. And that's a celebrated Komlosh, or if you want Banach-Zach theorem. However, I will explain later what is Banach-Zach theorem is actually a variant of this theorem when you assume that the functions are square integrable, or at least LP integrable, and the convergence, which is here, it holds in the norm of the corresponding LP. But let me explain. So Komlosh theorem tells you the following. Suppose that you have a sequence of functions bounded uniformly in L1. You know that a sequence of functions bounded uniformly in L1 may do two bad things. The first thing is that it may oscillate, like sinus and x, but it can also concentrate, because boundedness only in L1 could mean that the sequence will finally concentrate around one point as a kind of Dirac mass. And so there are many bad things that may happen to such a sequence. Still, Komlosh asserts that there is a subsequence. You can always find a subsequence such that if you take the Cesaro sums of this subsequence, then they converge to a function which is in L1, so it is integrable, and the convergence is almost everywhere. So it's like what we have here, but here, okay, the price to pay that these are not independent is that you have to take a subsequence. What is more, this property holds for any, there exists a subsequence such that any other subsequence has the same property and converges to the same limit. So that's Komlosh theorem. And so it clearly indicates that suppose that you have a method, numerical method, that produces only very poor what is called stability estimates, like LP estimates, and still computing averages, well, up to a subsequence, of course, which can be a nuisance for numerics, because you do really don't know if your method picks up the right subsequence. The averages converge almost everywhere, so it's again something you can compute. So the idea was that somehow maybe the averages, maybe this is a good assumption. Maybe one can assume that for a given method, this is always true. And then let's try to get some results. So that's what's behind what we call S-convergence, but let's proceed. There is still another example of this averaging, and that goes to dynamical system theory, the so-called ergodic hypothesis. Well, so assume that you have a dynamical system which is a mapping from the time interval 0 to plus infinity to some phase space. And well, it should have a semi-group property, but it's not necessarily the conditions we need now. And you can define an omega limit set of such a trajectory, which is simply a limit of all sequences of times for which the limit of UTN exists in a given space X. Now, the ergodic hypothesis tells you that, well, if you have any trajectory here, or maybe almost any, but let's start with any, and you take a Borel function only, if you're happy with continuous functions, let's start with continuous functions. And you take this integral average and you divide by the length of the integral. This is a continuous analog of the sum we have seen on the previous slide. It's like instead of taking discrete values, we take on continuum of values, we integrate and we divide by the length of the integral. So it's exactly the same averaging. And the claim is, well, that's a hypothesis, of course, it's difficult to verify for given dynamical system, is that, well, this limit actually exists for any Borel function f and converges to some function, or maybe even constant, depending on how you state your ergodic hypothesis, but we would be happy with a function here. And now there is a celebrated Birkhoff-Khinchin theorem, which tells you that actually if you tease a so-called stationary process, now everything is getting mixed up like, well, a priori this dynamical system is not a random dynamical system. So what I mean by stationary process, well, by stationary process, it's usually meant that there exists a measure which is sitting on the set of global trajectories, which are trajectories defined on the whole real line, such that, so there is a measure sitting on that, which is shift invariant, which means that if I shift my trajectory by some time, but I do it, I mean, it should be like stationary, meaning I should pick up finite number of times and shift all of them by the same value, then the value of the measure, I mean, the measure of the set is the same. If I can define such a measure and find such a set, I call this stationary process, and the celebrated Birkhoff-Khinchin theorem tells you that for such a process, the ergodic averages indeed converge. So again, this is a kind of sufficient conditions for these averages to converge, and this was also a kind of inspiration for us later on when inventing some sufficient criteria for convergence of these averages. Well, so the basic idea of S convergence is to replace the technique of Young measures by something which is more likely to converge without picking up a subsequence. Let me show you a classical example, which is something very, very simple, but of course you can think about more sophisticated things. Take a very simple function, un, I mean, there's a sequence which assigns, when n is odd, un is equal to 1, when n is even, un is equal to -1, right? This is a very simple sequence of functions that is oscillatory. It oscillates between -1 and 1. It doesn't have a weak limit, obviously. So let's speak about Young measures. I mean, how can we characterize oscillations of this sequence? Well, intuitively, everybody would say, well, the measure that characterizes somehow the behavior of this sequence, it's a measure which is sitting since the sequence spends basically the same time close to the level 1 and the same time close or equal to the level -1. Apparently, a good candidate of a measure that characterizes the long time behavior of such a sequence is a probability measure, which with probability 1/2 is sitting on 1. So it's a Dirac mass multiplied at 1 multiplied by 1/2 plus a Dirac mass sitting at -1 multiplied by 1/2. Right? That's what you would expect to be a correct limit of that. Well, if you think about Young measure, however, you will get a different answer. The Young measure theory tells you, oh no, that's not like that. This is not a Young measure associated to this sequence. You should pick up a subsequence. The theory of Young measure tells you, well, there is a subsequence such that it generates a measure. Well, here it's obvious. You take a subsequence consisting of only odd numbers here, you converge strongly to 1. And so for this particular subsequence, your Young measure is Dirac mass sitting on 1. For another subsequence, which consists of even numbers, you get a Dirac mass sitting on -1. And that's it. So this is what so you have like two Young measures. Both of them depends on which subsequence you pick up. And clearly you have the feeling that's not a good limit. In particular, imagining that this is a kind of numerical result. What if we do averaging? So again, we take our sequence and we replace it by the associated probability measure. So for a deterministic sequence, it's obviously Dirac mass sitting on the point UN. Also, it's a parameterized measure for each, well, here we don't have really dependence on Tx, they are like constant. So we take this, and now I take the average as in Komlow's theorem. Well, it's not so difficult to check that the average, so this is a measure now because it's a convex combination of Dirac masses. It's a non-trivial measure. It's not a one-point measure. It's a measure which is sitting on n points, and they are weighted, these Dirac masses are weighted by 1/n. So this is a non-trivial measure. Well, in the weak sense of measures, in the sense of weak convergence of measures, you can check easily that actually the limit of this exists, and it's exactly what you would expect. It's 1/2 of Dirac -1, 1/2 of Dirac 1. And it's if you want, it converges. These are like probability measures converging narrowly to this. And what is more, you can make it more sophisticated. You can take a kind of weight function here. So instead of having one, you take something which is obtained as a rescaling of an integrable function and dividing by the average of the integrable function. So again, the sum of these indices is equal to, divided by this is equal to 1. And the sum will converge to the same value independently of your choice of W. So I would say, well, W must be C1 integrable function that's positive everywhere. So in a way, the feeling is that the Young measure approach is not a good one. I mean, you should replace it by something like considering weights there. And that's really the idea of S convergence. Okay, let's abandon this now and let's go to Euler, because this is a kind of motivation for what we will do at the level of S convergence. So let's look at the Euler system of gas dynamics. So it's a problem, it's a kind of iconic example of a hyperbolic conservation law. There are 3 equations. Of course, you can have more, but I'm happy with 3 equations. I'm sorry, there is no blackboard here, so I cannot write on the blackboard, but we're trying to explain on the slides. I think most of you already know what I'm talking about. So that's a description of a compressible fluid that is perfect. Perfect means that the fluid is not viscous, there is no viscosity. And accordingly, the fluid is also not heat conductive. There is no heat conductivity included in the model. So it's a perfect fluid. As we know, nobody is perfect. So as each model that models something perfect, real fluids will never behave like that. But assume there is a perfect fluid. So the first equation, rho is the density of the fluid and m is momentum. Maybe you prefer to speak about velocity, u, but the velocity is rho, m is rho times u. The reason why I take m is that m actually is a conservative variable, because in the second equation we see it under the time derivative sign. If I take u, I would have rho u, so it's not really a conservative variable. And also in the context of Euler system, you cannot exclude the situation when rho may vanish, which means there is a vacuum in your fluid or gas. And in such a case, of course, u, the velocity is not really well defined. I mean, it's not really correct to say it is 0, because the velocity of the vacuum doesn't really make sense. So that's the reason why it's better to work with m. But later on, we will also see that m is more convenient variable from other reasons. Well, there is a momentum balance, or Newton's second law, which is conservation of momentum. Now there is a new variable called pressure. And there is nothing else. I do not consider any external forces and any viscosity. And so you see there is still, we have 2, here there are like 3 unknowns, but only 2 equations. So we have to add 1 more equation. This equation is a so-called energy balance, or if you want, first law of thermodynamics, which can be written in this form. When, however, there is a new unknown, which is the energy E, total energy of the fluid. So again, you see that we have still 3 equations, but we have like 4 unknowns. So there is more unknowns than equations. So we have to do something, and this is something what I do on the next slide. For the time being, let me say that, well, if this is a fluid which is confined to a, say, bounded domain, it's also good to prescribe some boundary conditions, because, of course, the behavior of the fluid depends if the boundary is permeable or not permeable. So I will assume that the boundary is perfectly impermeable, so there is no flow of the fluid through the boundary. The fluid is tangential to the boundary. So this is this condition. Right now we know that we have to supplement this by some other relations, but because this is not a formally well-posed system. So these are the so-called constitutive relations. We write down the kinetic energy, I mean the energy in the form of kinetic energy plus internal energy. And for the internal energy, we assume there is an equation of state which relates it to the pressure. Now immediately you see that we already have like 3 equations for 3 variables, and so we are okay. If I assume this, in addition, I can define also the entropy, which is the following quantity, where S is any function of this P over rho gamma. Gamma is this gamma which is sitting here. And this quantity is called total entropy. We will see it later. And so in the best known example of in gas dynamics, which is the so-called Boyle-Mariotte law, the entropy just takes this form. And then you can supplement your system, Euler's system that was on the previous slide, by formulation of the second law of thermodynamics. You can compute actually that, well, this relation here for the total entropy will be satisfied with an equality sign, provided all quantities here are smooth, provided all of them are continuously differentiable. Then this you can derive it from the previous three equations. There is no problem. However, in the context of weak solutions, we will be speaking about you should replace it by inequality, because for the weak solution this is not automatic, and this is usually added to the system as an inequality, which is like formulation of the second law of thermodynamics, which means that the entropy is always being produced. There is nothing like the system cannot decrease entropy. So this inequality corresponds to some source term in the entropy equation. We may not know a priori, but which is a kind of what is called admissibility condition. It was actually assumed that this is a good condition and will pick up a good solution among all weak solutions, which is not true actually. Well, what is more, and what I assume here is the hypothesis of thermodynamic stability. It can be expressed in this way. I can introduce, or I have introduced on the previous slide, I have introduced also the temperature. So in the standard variables, which is rho and theta, the hypothesis of thermodynamic stability tells you that the pressure is an increasing function of rho and internal energy is an increasing function of theta. And actually this value here is called positive compressibility. So this condition corresponds to positive compressibility. This condition corresponds to a positive specific heat at constant volume. And if this is satisfied, which as you may see, it's obviously satisfied in the case of Boyle-Mariotte law, then we speak about thermodynamically stable system. And now you see why entropy or conservative variables are better, because if I take now rho m and total entropy as my new variables, and I write the energy in terms of these three variables, then the energy happens to be a convex function of these as soon as we have thermodynamics. So these two properties are actually equivalent. And so convexity of the energy is important because in the weak formulation, usually functions are only weakly continuous in time. And so thermodynamic stability means that if you choose the right variables, which is rho m and s, then this quantity is going to be weakly lower semi-continuous in time. And that's a property which plays some role in the analysis. Well, what do we know about Euler's system? Well, these are well-known facts, so let me go fast. We know there are classical solutions. If you start with nice initial data, meaning C1 initial data, maybe you need a little bit more. There exists a short time interval on which you have a smooth solution. That's fine. However, what is also known is that, well, this time could be short in a way that after a finite time, the solution will develop singularity. They are called shock waves. And this is a well-known fact. This is not like a hypothetical assumption that because mathematicians are not able to show that the solution is regular. No, solution indeed becomes irregular after a finite time, at least for certain initial data. And so if you want to continue, you have to switch to a more general. So these solutions, shock waves, they do not have derivatives in general, not at any point. So you cannot work with derivatives. So you no longer have this formulation of the problem in terms of classical PDEs. You have to switch to the weak formulation. So you replace all derivatives by distribution derivatives, which means that you transfer all derivatives on the test functions, and you obtain a weak solution. Now, the unpleasant feature of weak solutions is that actually they are not uniquely determined by the initial data. And this is also known for quite a long time, maybe 50 years or more, that you can find initial data for which the problem admits infinitely many weak solutions. What is less obvious that you can do it in the class of admissible weak solutions. This is much more recent, which means that even if you admit, if you consider only weak solutions that do satisfy the entropy inequality, then you still have infinitely many of them. These are more recent results based on the theory of convex integration that was developed by Camilo Delelis and Laszlo Szekelydi and many other people recently, Vlad Dikol and Tristan Buckmaster and others. Paul Isset, of course. Okay, so this is the truth about weak solutions. What is more, the numerical methods, usually it's difficult to show, to prove that they identify a weak solution. We will actually see that if the numerical methods converges to a weak solution, then actually the convergence must be strong. But we have very poor a priori bounds. We cannot do much, we cannot get very good a priori bounds for numerical solutions because the solutions of the target system, they do not have derivatives. So you do not expect, the weak solutions in general, they do not have derivatives. So you do not expect to get bounds on your approximations in terms of Sobolev norms, because you simply, the Sobolev norms must blow up if you converge to a solution of Euler, which is a weak solution. So we have only estimates in terms of LP norm, and this is not enough to prevent oscillations and even concentrations. And so it's, from the numerical point of view, at least from the point of view of an analysis, is more convenient to introduce some kind of generalized solutions. You may call them oscillatory solutions. They are usually characterized by measures like Young measure I was speaking about on some of these previous slides, and they are called measure value solutions, and you can even develop something more general, what we call dissipative solutions and so on. So all of them are somehow related to the fact how well you can describe weak limits. So what is a good approximation? Actually, in numerics, people usually speak about consistent approximation. Consistent approximation is an approximation of the problem where the equations are almost satisfied with some errors. So consistent approximation in the context of Euler system is that we have equations satisfied in the weak sense. So on the left-hand side, you have the Euler system, and on the right-hand side, you do not have zero. If you had zero, you would have Euler system. I also include the entropy here. You assume that there is some error term, but the error term, so you have a sequence of solutions, and the error term is supposed to disappear in the limit. So when n goes to infinity, the error term, in the distributional sense, in a very weak sense, should disappear. So in the limit, you should get zero on the right-hand side, which means you expect somehow that the limit will be a solution of the problem, but that's not obvious because, of course, these functions will converge only weakly, because what we have at our disposal is only this kind of estimates. We can assume that the energy is bounded uniformly. That's something you can derive. You can also derive with some effort that the entropy is bounded from below uniformly in time. So these two estimates should be enough in order to prove convergence, but as we know, they are not enough. So what may happen? Well, first of all, there are examples of consistent approximations like vanishing dissipation limit. I'm not necessarily speaking about numerical solutions, right? My consistent approximation can be vanishing dissipation limit, meaning the limit of the Navier-Stokes-Fourier system, and could be also limit of numerical schemes, in particular those that dissipate entropy and preserve or dissipate energy. And there are several that do this, Flachs, Friedrich, Rusanov, and there is a scheme we developed with Maria Lukacheva and Hanna Mizerova, which is based on the so-called Brenner model. Now, so the consistent approximation, the best thing you can expect is this. Don't be perplexed by these stars and fancy spaces. This is weak convergence. Roughly speaking, the functions do not converge almost everywhere. They converge only in the sense of integral averages. If you take integral average of this, then it will converge to the integral average of the limit. This is called weak convergence in the LP spaces. And in particular, you do not know if the limit is a solution of the Euler system, even not a weak solution. You have to introduce some kind of generalized solution, which I will discuss later. Dissipative, which we call dissipative solution. They satisfy a kind of entropy inequality. And the limit is only a generalized solution. And in particular, they can oscillate. So you may think about Young measure, which is generated by this limit. then the Young measure could be a measure value solution of the problem. However, I try to convince you that the Young measure is not a good object to study. So we will do something else. Well, so what may happen? There are three cases where you see strong convergence. And so you basically don't see any kind of oscillations, but these are very exceptional cases. The first case is when the limit system or the Euler system has a smooth solution. Well, this is not always true, as we know, and in particular, it is not true on long time intervals. However, in some examples, for instance, in meteorology, people do not expect to see shock waves. And so you may expect that the limit has a smooth solution. In that case, well, the consistent approximation will converge strongly. That's something what we can show, and it is a kind of not completely obvious result. You have to pass via a generalized solution, then you have to show something what's called generalized weak-strong uniqueness principle. So basically you show that your consistent limit is a kind of generalized solution, and it belongs to the class of generalized solution that they comply with the weak-strong uniqueness property, which means that if the same problem has a smooth solution, then the generalized solution coincides with the smooth solution. The same happens when you know that the limit is smooth. Please note that there is a tiny difference between these two results, although they may look the same. Here, I do not assume anything about the existence of the solution for the limit system. However, I assume that my limit is a C1 function, which may be the case. Well, if this is the case, then the limit is necessarily a strong solution of the Euler system, and the convergence is strong. We don't need any subsequence, and we converge strongly. So again, we don't need any Young measure, and we have unconditional convergence. The right result, the last result is a kind of surprising, and it takes some time to prove it. Actually, assume now, again, let me warn you, what I'm assuming now is that the limit I get, the weak limit I get out of my consistent approximation, that could be a limit of, say, numerical sequence, is a weak solution. Assume I know that. I mean, I'm not saying anything about, I'm not assuming the Euler system has a weak solution. I assume that my limit is a weak solution of the Euler system. Well, this implies that convergence must be strong. This is a result we proved with Martina Hofmanova. So this means that actually there is, if I exaggerate, there is nothing like a weak convergence to a weak solution. If you see weak convergence of an approximate sequence, a numerical sequence of Euler, the limit is definitely not a weak solution. You forget weak solution. Either the convergence is nice and in always is strong, then you don't need any Young measure. Or if you believe in Young measures in weak convergence, then the object is not a weak solution. You have to work with generalized solutions. So that summarize here. So the weak convergence occur if the limit system does not have strong solution, the limit is not C1, and the limit is not a weak solution. Well, so what happens if all this is true? You have weak convergence. Weak convergence may have these two unpleasant features. The first one is that the functions may oscillate as sinus and x, but they may also concentrate as this sequence here, which means it's a rescaled sequence of a given function, which is non-negative. It's like this is like a sequence of regularizing kernels. We know that it's bounded in L1. Actually, the integral is always 1. But the weak limit is not a function, it's a measure, it's a Dirac mass sitting at 0. So these two bad things may occur for a sequence for approximate sequence of the Euler problem. So you would like to see how these solutions look like, in particular how the limit oscillates, and for that people introduce the Young measures. So the Young measure assumes that you have for each function b you have a subsequence which converges weakly. And so the weak limit represents a kind of function which to each function b assigns this limit at any point tx. And so, as we know, this is a linear mapping defined on the set of continuous functions with compact support. And so it can be characterized by a measure. And this measure is called Young measure. But the problem is that you have to pick up a subsequence. And we have seen that's not always relevant. And the Young measure sometimes describes the oscillatory behavior of the sequence. Now we would say, well, I would like to see it, how the measure looks like, in particular, how this limit looks like for some specific B's. For instance, you may be interested in barycenter, which corresponds to taking, which is actually the weak limit, which corresponds to taking B to be identity. Or you may be interested in deviation or variation of the measure, whatever. How you can compute it? If you compute it like classically, which means you take the sequence, you will never see anything because the sequence is oscillating. I mean, that's not by chance. It's just because we are computing Young measure, the sequence must be oscillating. And so if you compute it classically numerically, you will see oscillations, you will not see anything. I mean, you will not identify anything. And so that's why I introduce a different approach, which is based on S-convergence. Finally, we come to S-convergence. Well, I still have 20 minutes, so I hope not to speak too much over time. No, I will finish in 20 minutes. So what is S-convergence? Well, that's the definition. Later on, we will see that actually the definition is equivalent to something I would like to have. So we have now considered a general sequence. You do not have to think about anything like a consistent approximation. Let's just take a general sequence of functions. Well, we say that the sequence is S-convergent if for any B, for any function B, like similar to the functions we have seen on the previous slide, compactly supported, sitting on the range of this sequence, you take what probabilistic people would call, say, correlation. So you take B of un and you take another index um, and you compute this integral. This is a number. And now you average it, you take the Cesaro averages on this, and you want that this limit, if you take the limit with respect to only one index here, that the limit exists. This for any m. And this is actually much stronger than assuming that B of un converges weakly, because if B of un converges weakly, this limit obviously exists. We want a kind of weak convergence, but average weak convergence. So in particular, this means that, well, maybe the sequence contains some bad points where they are not really good from the point of view of convergence, because maybe the computation was done wrongly, but taking averages, you eliminate it. So this is where we will see, I will be more specific later. So I assume this, and I also assume that if I take this sequence for a fixed m, and now you take the same limit, but now take the limit with respect to m, or I do it like at the same time, I take the limit when nm goes to capital N simultaneously, and I take the limit when this n goes to infinity and divide by n squared, that I get the same. This is my definition of S-convergence. We will see later what are necessary conditions for that. I mean, it looks like now it's a little bit funny, right? What it means. Well, it turns out that the S-convergence is equivalent to the property we need. Meaning, if I have an S-convergent sequence, it is the same as saying that if you take a function B, the same one that was on the previous slide, and you take the Cesaro average of this, B of un, and then this average will converge to something what I denote B of u bar. And in what is more, the convergence will be strong in L1. Actually, if since B is bounded, it will be strong in any LP with any finite P. And so in particular, if this is a numerical sequence, I mean, you can see the limit because the convergence is strong. And the limit, let me point out, this is, so the limit again can be seen as a mapping for each point tx. This is a mapping which assigns to a continuous function b this value, and so it's a measure. And it's not the Young measure in general, it's a measure which is generated by Cesaro averages. And so my claim is that numerical sequences are more likely to generate these measures than Young measures, because here if you have something bad, you can eliminate it by averaging. And so this sequence, we call it S-limit. And it's a parameterized measure similarly to the Young measure, but it's not a classical Young measure. And this is the limit of the S-convergence, right? So it's a sample of measures. In certain cases, there are probability measures. You need a little bit more. Assuming un, you need equi-integrability, you need uniform L1 norm of un being bounded. And you speak about this limit as a measure. So it's a kind of object that characterizes the solution. You can compute this measure in the sense of Wasserstein distance, which is very good because now you can compute it because the convergence will be strong. You take the Wasserstein distance again. I don't have time to explain what it is. It's basically a metric in the weak topology of measures, but it's a little bit exaggerated statement what I'm saying now. So you take this convex combination of Dirac masses, which are measures sitting on the approximate solutions on the S convergent sequence. You take this Cesaro average, and you measure the Wasserstein distance from the limit, from this limit here at each point y, because at each point y we have this and we have the limit. And now you compute the LS norm with respect to y, with respect to the space-time variable in the context of Euler system, and you will find out this converges. So we have strong convergence in LS or in the Wasserstein distance, so you can really see what the measure is. So you can compute it. So that's the advantage of having S convergence, right? So we say that basically if S convergence is the same as that these limits exist. Still, we do not see what would be a kind of good sufficient condition. I will show you some later. Well, now, so the basic properties. The first property of S convergence is that it is somehow robust with respect to what is called statistical perturbation. And that's exactly what may be relevant in numerics. You have two sequences, and I will assume that they are what is called S equivalent. By S equivalent I mean that, well, whatever small epsilon is, you take the points n where these two sequences are different in the sense of L1 norm. So I take the L1 distance between these two, and I take all points where this distance is bigger than this epsilon. In all other points, the distance is smaller than epsilon. I take all these points, I compute them, this symbol means the number of these, and I divide them by total number of n's in the interval 0, n. And I assume that this goes to 0 when n goes to infinity for any positive epsilon. So in other words, if these two sequences do not differ on many indices, they are this is called statistical equivalence. Now, S convergence is robust with respect to statistical equivalence, meaning if I have two sequences that are statistically equivalent and one of them S converges, then the other one must also S converge and converges to the same limit. There is a trivial but useful corollary, because you may think, well, maybe I'm losing something if I use S convergence, if I have strongly convergent sequence. Well, that's not true. If you have a sequence that converges strongly to a limit in L1, then it converges, S converges in the sense of my definition to the Dirac mass sitting on this limit. So you get exactly what you expect to get, right? So you do not get any fancy object. You just get the limit, which is the strong limit. There are other properties. Well, S convergence actually works for stationary sequences. However, let me warn you that it's really very dangerous to assume that a numerical sequence is going to be stationary. What I mean stationary? Stationarity is, again, a concept borrowed from probability. However, keep in mind that in the context, for instance, of numerical solutions of Euler system, stationarity has nothing, there is no, well, what I mean by probability is actually the space of time and X. So my Q here is time space. It's not a space of probability. It's not a probability space, but there is a certain analogy. But numerical sequence will definitely not be stationary, but it might be asymptotically stationary. So what is stationarity? Stationary means that you have a sequence, you take its value at the point K1 up to Kj. You take a finite number of points, and then you shift them by the same distance, by n, all right? And if you compute what in probability is called law, which means a distributional function of this, it must be the same as the distributional function of the shifted sequence, which is like in probability, you would say that the joint law of this is the same as the joint law of this. And this can be mathematically expressed as taking any, say, again, continuous functions and computing these integrals, which in probability you would call it expectation. right? And you assume that these are the same for any B. That's definitely not to be, this will mean not true for any numerical sequence. However, you may still hope that asymptotically you will be close to such a sequence. And then you have celebrated Birhoff-Khinchin theorem, which tells you that, well, such a sequence, stationary sequence, stationary in this sense, converges almost everywhere. That's Birhoff-Khinchin ergodic theorem. So it is S-convergent. So stationary sequences are S-convergent. Well, so we try to find something weaker, of course, because assuming stationarity, this is not very likely to hold for sequence of numerical solutions. We came up with something that we call asymptotic stationarity. Let me show you the definition. It looks like more convincing that maybe something like that is likely to be true. However, you have to refine it a little bit, but I do not want to speak about it. But this is one of the sufficient conditions for having S-convergent. What is asymptotic stationarity? Well, you still assume this, that the correlation limit exists. That's not a strong assumption. That's something you would agree that should be true. Well, of course, there is no proof. If you give me a sequence of numerical solutions, I cannot prove it, but let's assume this is easy. What's not so obvious is what is called asymptotic correlation stationarity, which means I take two iterations, K1, K2, I take a function B and I compute, again in probability, they would say that you are computing correlation of this, and you subtract the same thing when I shift everything by n. So it means that, well, intuitively you would expect if K is big, right? If you assume that this is an approximation of something, if K is big and if n is also big, or K1 plus n is also big, then this should be more or the same, right? I mean, for instance, if the sequence converges strongly, it is the same. So our assumption is that, well, it's not the same, but it's very small if K is large. So it goes to 0 for any fixed B when K is large. This is what we call asymptotic correlation stationarity. And well, the result, the theorem is that, well, if you have asymptotically stationary sequence, then it is S-convergent. Let me remind you before I come back to the Euler system that actually Boulder proved about the following. Well, he proved a result in terms of Young measures, but it also can be interpreted in terms of S-convergence. If you have a sequence of functions which is kind of uniformly L1 and integrable, so equi-integrable if you want, then there is a S-convergent subsequence. However, we don't like this. Well, we don't like this result is not of use in numerics because the point is that you have to pass the subsequence, and that's something what we somehow believe that in numerics we get S-convergence without passing to subsequence. Well, so let me reformulate what I said in the abstract setting. Assume that I have, this is my assumption, assume that I have S-convergent consistent approximation. You may think about this as being numerical solutions. Assume we have that. We know there are some sufficient conditions like asymptotic stationarity or asymptotic correlation stationarity that will guarantee this. Of course, if you want to verify that this is true for a numerical method, it will be extremely difficult. But assume we have that because we are averaging. Well, then, well, the first is that you can show that the limit is kind of new. The limit, it's not a Young measure, right? It's a measure which is obtained from S-convergent. This is the S limit of this sequence. It is something what you may see if you don't like to say dissipative. It's a measure value solution of the Euler system, whatever you understand by that. The convergence, so it's a kind of generalized solutions. In particular, it also satisfies the weak-strong uniqueness principle, which I speak later. We have convergence in Wasserstein distance, so you can really see this measure. You can compute it. If the limit system has a strong solution, then this measure is Dirac mass sitting on the strong solution. If the barycenter of this limit is a C1 function, then the limit again is a strong solution, and it's actually Dirac mass sitting on the strong solution. And if you happen to know that the barycenter of this measure is a weak solution to Euler, that's a rephrasing of the last result, then actually it's again a Dirac mass sitting on this solution, right? So these are the three cases where you get kind of strong convergence, which is, so what I want to say is you lose nothing passing to S convergence. As soon as you have these three nice cases, S convergence gives you exactly the same as you would like to have. In particular, if you believe that your numerical methods really generates a weak solution, then S convergence gives you the right limit, right? So you do not do anything fancy unless you do not converge to a weak solution, really. So these are the results for Euler. Let me finish my talk by what could be kind of improving convergence criteria. That's something what we are currently working on. So basically, you can you have seen that this asymptotic correlation stationarity, which still may not be true for some reasonable generating sequence. You can refine it. You can assume something less. Basically, you can define something what I call statistically significant set, which is the set of double indices, which is similar property we have seen in the definition of statistical equivalence. So you say you take all couples which are sitting in this set, and you take all of them that are smaller than n, and you divide by the total number of these n's, which is n squared. And again, you assume that, well, this thing is goes to 0 when n goes to infinity. And now the criterion is that, well, you assume again a kind of asymptotic stationarity for your sequence, but it's enough to have it satisfied out of this exceptional set. And this is much weaker, it's much weaker than what I had before. And this is again a sufficient condition for S convergence. And so, so if we have this, we still have S convergence of the sequence. Well, so to conclude, S convergence is a tool how to visualize or describe weakly converging sequences. A priori, we do not refer to any numerical method. It's just a sequence that converges weakly and where you would like to describe its statistical properties that are characterized by some measure, which we call S-limit. It's kind of analog of a Young measure, if you want, but it's obtained in a different way. It's obtained as a limit of convex combinations of the measures sitting on your approximate sequence. As such, the method can be convenient provided you believe that numerical methods for Euler system or other problems where oscillations may occur develop oscillations. Well, this you may believe, but you must believe at the same time that these oscillations are also physically relevant, which means that this is really what you want to compute. But there are groups of people like Eitan Tadmor, Sid Mishra, and others that really compute this. Well, as convergence gives you an efficient way how to compute them, how you see them. I leave apart the question whether or not this is what's really going on in the real world, right? As convergence doesn't give you an explanation of turbulence. It's just a mean how to describe oscillating sequences and how to describe them in numerical sequences, provided you believe that this is what you want to see. Okay, thanks a lot for your attention.
So thank you, Edward, for this wonderful talk. Now we have got some questions. So do you see Q&A section near the share screen option in your laptop?
Let me see. I should stop sharing, I think.
That doesn't matter.
I don't see anything without stopping. I think I will stop. Oh, yeah, I can see them. Yes, questions. Okay, there is a question. So let me go. So shall I go directly to the question? So the first question is the fact either the convergence is strong or the limit is not a weak solution only true in the full space or in bounded domains? Yes. So for the full system, for the full Euler system, the system that I presented, it is true on a bounded domain. On the full space, I suspect it's true. You have to provide sufficient boundary conditions at infinity. On the full space, it's actually a work in progress of a student of mine you might know, Neil Aziz, who is now in Berlin, who is working on it. So please don't start working on the same topic. Let me point out that if you take something what's called isentropic Euler, surprisingly, the result is not completely true on a bounded domain. You have to assume but it is true on the full space, provided you have sufficient, provided you fix suitable far field conditions. This is also in our paper with Martina Hofmanova that is now published, so you can download it, or if you cannot download it, I can send you. So for the isentropic case, on the contrary, the result is true on the full space, and it's true on the bounded domains under certain conditions. In the incompressible case, the result is not true. There is an example which you may find in the paper by Greengard and Thoman. It's an old paper from 80s. Well, now I may say it's old because it's 30 years, where they show that you have a sequence of solutions of incompressible Euler system. They are stationary solutions, which means they are independent of time. They are defined on a compact set. They have compact support. It's only velocity. It's incompressible Euler. So you have only sequence of velocities. They have compact support. In particular, they are solutions of the problem on sufficiently large bounded domain, and they converge weakly to 0. So you have a weakly converging sequence to 0. 0, of course, is a strong solution of Euler. So it's not true in the incompressible case. The second question is, is there any way to conclude that consistent approximations is weakly strongly S convergent? Well, I find it extremely difficult. We have full numerical evidence it is true, because, taking averages, you really eliminate some random errors that may be present in the sequence. Well, if you could prove it, say, for a given numerical method for Euler, the interesting case is a system where you really don't control the derivatives, right? So it's good. For Navier-Stokes, by the way, the results I spoke about, V convergence to weak, this is not true for Navier-Stokes. Don't be confused by that. It's true only for Euler. Well, at least we can prove it only for Euler, sorry. For Navier-Stokes, I'm not sure if it works. So here it's interesting to take Euler. Well, imagine that you could prove that there is a numerical method that is S-convergent. Well, then clearly this S-limit is a nice candidate for being a good solution of the problem, because S-convergence is like unconditional. You don't have to pick up a subsequence. So you would say, oh, this is the physical solution. The S-convergence would pick up for you the good solution. And so let's think in terms, let's forget numerics and let's think in terms of zero viscosity approximation. If you can show that there is an S-convergent sequence, which would mean, well, this is a good solution. We would have uniqueness, or at least some way how to pick up a good solution. So I think it should be extremely difficult. Maybe to understand better what the difficulty is, take a very, very special consistent approximation, which is a sequence of solutions of the same system. You take sequence of solutions of the Euler system itself. This is a consistent approximation because the consistency error is 0. You have solution of the system, and now we know by the theory of convex integration, well, that for given initial data, or at least for some initial data, the Euler system has infinitely many solutions, weak solutions that are admissible and start from the same initial data. Take any convex combination of them, it's a consistent approximation. So it's not as you do not get S convergence here, right? It's extremely difficult to prove it. The hope is that if you have a numerical method, you do not have solutions of Euler. You have something where you add viscosity. And so that's the idea, that somehow why people believe that the Navier-Stokes system where there is viscosity will pick up a good solution of Euler. So you may say, you may although there is no proof of that. But so you extrapolate and you say, well, maybe, if I take numerical method, which is taking extra viscosity, you may expect that numerical method gives you a unique solution, right? Numerical solution should be unique. Then you converge, maybe I pick up a good sequence that is as convergent. So there is maybe more chance, but if you can prove it, it would be really great. So that's, I think I was sufficiently clear why this is not an easy task. I think there are no more questions, right?
Okay, thank you, Edward. So I request participants to write the questions in question and answer box. And meanwhile, I think Professor Jua has a question. So let me try if I can get him, so he can ask the question you directly. So NDK, can you hear us?
Sorry, can we get God?
Yeah, I can hear.
Yeah, so please ask your question.
Oh, yeah. So thank you. Nice to see Edward again. Yeah, I was wondering myself, Edward. Maybe I had known this and I forgot. But is the fact that when the weak limit is a weak solution, then the convergence has to be strong. Is it known, for instance, in the classical theory of Khrushchev?
You mean for scalar conservation laws?
As multidimensional scalar conservation laws. I mean, of course, there you can also.
I mean, finally you get also you get always strong convergence. Like, I mean, if you have admissible solutions.
But is there an argument saying that whenever a numerical scheme converges to a weak solution, then it has to converge strongly?
I don't know. I don't know any arguments of this kind. We try to prove it. I can try to prove it if you want, but we try to prove it for Euler. As I try to explain, it's not even true for incompressible Euler. Of course, incompressible Euler is not a hyperbolic system,
So normally, of course, for conservation laws, people try always to get the entropy solution. Then they make the numerical scheme to be entropic, and then you have a compactness, basically, right?
That's
but
true.
You could ask the question, as you said, you could simply say, take a conservation law. Suppose I have a numerical approximation that converges to something that is simply a weak solution, not necessarily the entropic one. Is this necessarily a strongly convergent sequence?
I don't think you can prove it in the full generality. Actually, the proof uses the fact, for instance, for isentropic Euler, we can prove it only on the whole space, actually, with sufficiently, with some far field conditions. And the point is that you do not assume anything about the data. For the isentropic case, you do not assume the initial data converge strongly. Still, you have this result. So I think that's why this is strong. And for the isentropic Euler, it uses the fact that if you compute what's called oscillation defect, it's a positively definite matrix valued measure. And since you are on the full space, you get something like Liouville's principle, which tells you that such a measure must be zero. And so I don't think you can do it. And this is really based on the structure of nonlinearities. For instance, if the pressure is not a convex function, I have to assume for the isentropic case that the pressure is a convex function, like rho to the power gamma. If it's not a convex function, I cannot prove it. So I would suspect that it's not so clear for scalar conservation law.
Thank you. Thank you.
Okay, so thank you, Edward. I don't think we have other questions. So we thank you, Edward, for this wonderful talk.
For the invitation, it was my pleasure.
Thank you, Edward. Thank you.
Okay.
So before closing this session, I would request Prosenjit for any announcement.
Yeah.
Okay, so I leave now, right? And we discuss later. That's what you wanted, Ujjwal, right?
Yeah, sure, Edward. Okay.
Should I leave right now?
Yes, please.
Okay, I leave the session then.
Yeah, so I'll just make an announcement for the audience and close the session.
Mm-hmm.
So for our next talk is by Professor Helge Holden on next Tuesday on Kasama Holm equations. And I hope everybody enjoyed Professor Eduardo Ferizal's talk thoroughly. We thank Professor Ferizal for this wonderful talk. And we meet you all in next Tuesday.
Okay.
And I request all the participants to leave the platform now.